Hi, Victoria. How are you?
Hey, buenos dias. You?
Happy Monday.
Yes, happy Monday.
Indeed, it is. Welcome everyone. We'll start in around 5 to 10 minutes.
Or 11?
Yep. Thank you for coming. That's true. I usually open and I always say the same things. I usually open.
Hello, everyone.
Good morning, Jamie. Another early bird.
Hope you're all well.
How's guitar?
Very well, thank you.
Maybe?
How's the weather?
Oh, sorry, Katarina.
Oh, no, go ahead. Hi,
Oh,
Federico.
good morning.
Federico. Am I saying the name right? I want to make sure. To unmute, it's, yeah, there you go.
Yes, hello. Yes, now it's correct. It's Federico, indeed. Thank you.
Yeah, thank you. I wrote in the email Frederico. In Portuguese, we sometimes spell it that way, and kind of I spelled the name wrong. So I'm sorry about that. And thank you for coming. Thanks.
Very welcome, Doctor. It's lovely to hear. Thank you very much for coming.
Good
Is the
morning,
weather?
Federico.
Oh, go ahead.
I'm
Sorry.
finished. I was just greeting.
Is the weather still rainy in Switzerland, or is it better?
Oh, right now it's excellent, and the whole weekend has been fantastic. So
Oh, perfect.
everything is good.
I'm glad to hear. We had the guest speaker last week, right? It was beginning of last week or last weekend. That said that the weather has been horrible, rainy, but I'm glad it improves. It improved.
So, who saw the moon last night?
Well, I didn't. But is it everywhere that you have the? I think it's.
Well, I looked. Yeah, it was. You could see it from what I just looked in Europe and across North America, but it looked as though, but it sounds like people did not witness the total lunar eclipse. It was we had a beautiful sky. It was partially cloudy and really, for some reason, I don't know, it was like this beautiful midnight blue. But the patches that had sky didn't have the moon in them. And I was looking at the right time. I really like to witness the celestial events, but anyone else?
Yeah, I like witnessing them too. It was very cloudy here, so I don't think we would have seen it that long.
Yeah,
But I saw one's solar eclipse when I was still a student in Germany. We had in Europe solar
when
eclipse.
I saw one in Germany too.
Oh, I don't know,
It was
2000 or
yeah,
99 or
yeah,
something.
yeah,
Yeah,
yeah. We saw
exactly.
the same one. It's so exciting.
Oh, you were in Germany too? That's
Yeah,
so
we went to
exciting.
Germany to see the eclipse.
Oh, you went there. Oh, interesting.
Yes,
Yeah, I was
to
there.
Germany. It was really sweet because everybody had their solar viewing glasses on. And so it felt kind of like a bonding experience because everybody just came outside and, sat on the park benches or wherever they were. And it was long enough that we drove to a second location and just parked on, like tried to follow the eclipse.
Oh,
And
that's
it was so fun. It was so
And
pretty.
there was a partial one here in the US a few years ago when I was at Stony Brook
Oh, we
University.
had a total and it went exactly through my city. And so I
Oh,
had a
wow.
bunch of people come and we actually watched it from my driveway. Had people staying here. And it was amazing to have such an exciting thing just happen right on the drive, right. Yeah, it was total here. And the thing was really that I remember so much more than visually was that the temperature changed dramatically. It was warm, and then it was almost like walking into a refrigerator. It wasn't like it was chilly, but it was a different kind of, it was different. It just, you could feel it on your skin. I loved that eclipse. Did you notice that? Were you had it partially where you were, right?
At Stony Brook, yeah, I didn't notice any temperature change, but it's pretty humid. I think it was kind of summer. What
Yeah.
season was it?
Yeah.
I forgot, but it's pretty humid, so I don't think, yeah, and the partial one, I don't think you feel it that much, but yeah, it's interesting. We'll start in around 5 minutes. Welcome everyone. Thank you for being patient and waiting here, everyone in the audience, and thank you for the Federico for coming. We are very excited for your talk. It's yeah, it's a very exciting time, and we will have a lot of questions when we can basically start using this and solve all of the issues of humanity. So it's
Right.
amazing that you work in that field, and it's a
Yeah,
great honor to have you here.
it is such an honor. And the sun is fusion. So it's kind of a related topic,
Yeah,
eclipse and all.
definitely. Yep.
I was reading your paper, Doctor, and the amount that I could understand looked ingenious to me. Just your problem solving solution to some of these issues that I think you were having with dealing with the plasma. I'm very very much looking forward to this talk.
Thank you. I hope you'll find it interesting, and I hope I'll be able to explain it in a way that's understandable for everybody.
Oh, thank you so much. Yeah, it's the challenges that maybe are the particularly interesting parts.
I was actually quoting parts of the paper to Katerina earlier, and I was by the I'm Jamie, by the way, and I was saying to her, how cool does that sound? Like dealing with plasma controls and everything. That just sounds so amazing.
Now I'm curious which part of the paper you were citing.
Um, let me see. Katerina, which part was it? It was literally just a line talking about how your experiments, all your experiments were dealing with um,
Oh,
magnetically. Uh-huh. You
you
got it?
want me to read it?
Yeah. Just the part.
Each experiment begins with standard plasma formation procedures. And
Just even
love
that little
how
part.
does that sentence sound from the paper. It is true, it does sound amazing.
Just straight away, just that's a small line, and already I'm thinking, wow, how cool is that?
Yeah, I realize these things are indeed very cool. If you look at it, if you hear these things for the first time, it's really strange actually how used you also get to these things. Like we have a tokamak in our lab here at the university in Switzerland at EPFL, and we make these kind of plasmas like 30 times per day. So all of a sudden, if you see them the first time, I remember seeing my first plasma, I was really excited, and somehow it's also something that you get used to. So it's good also to hear how exciting it sounds for people who maybe don't get to deal with these things every day.
Yeah, I even had to look up exactly what that machine was that you're talking about. Is it Takamura machine? Yeah.
Yeah, it's called
Um,
tokamak. I'll tell more about this
Tokamak,
during
sorry, beg your
the
pardon.
talk.
Tokamak, yeah. And the different shapes that you were making from it, which, like, of course, you'll get to all of this, but as I said, very exciting. Very much enjoyed the paper.
Okay, I think we can slowly start by introducing you, and then we'll go from there. Um, So welcome everyone to the Science Society. Happy Monday, everyone. And we are very excited to have here our special guest, Dr. Federico Felici. And he will talk about the the paper that was recently published, and the title is Magnetic Control of Tokamak Plasmas Through Deep Reinforcement Learning. And let me give you a little bit of background information. Dr. Federico Felici is a research scientist at the Swiss Plasma Center at EPFL Lausanne. He holds a master's degree in systems and control from Delft University of Technology and a PhD in plasma physics from the Swiss Plasma Center at the EPFL Switzerland. And his research interests include all aspects of tokamak plasma control, in particular control-oriented modeling, model-based controller design, and integration of control solutions on current and future devices. So thank you so much. He also won several awards. One is the award for best PhD thesis of his year, and so we are very honored to have you here, because your work, if you're successful, you will solve all the problems of humanity. So it's a very big deal and special honor to have you here today. And Victoria, go ahead with your questions. Thank you.
All right. Thank you, Katarina. Excuse me. Yes, Dr. Felici, Science Society welcomes you. We're so happy to have you here, and really looking forward to learning about your research into nuclear fusion using magnetic confinement, and also what this could mean, as Katarina said, toward a promising path towards sustainable energy. So yay. Um, and about you, beyond hearing about your research, we like to make a path toward really welcoming you and introducing you to our audience. And so it's interesting to learn about people's different connections to science. So my question to you is, looking back through your life, can you reflect on a moment or experience, maybe a relative or a class or something that happened that may have provided the spark of curiosity that has developed into your interest in science?
Thank you for your question. Yeah, I'm very happy to be here. Thank you very much for the introduction. It's really I'm really happy. It's really an honor to be talking to you about all this exciting work. Yeah, I'm happy to start by answering your first question. I mean, I don't know when I actually decided I wanted to be a scientist. It's something that came kind of naturally at the beginning from, a natural inclination in high school. I liked physics and I liked math and these sorts of things. And maybe one interesting part is that I also liked science fiction very much. As a kid, I watched kids like Star Trek: The Next Generation and TV shows like kind of like that. And I was always interested in this kind of technology, the fact that you could just use technology to solve problems, difficult problems that you always had some kind of technological solution. And while I realized, of course, it's just science fiction, so it's just a TV show, there was something about this kind of optimism about solving humanity's problems in the future through technology, which I think really spoke to me. Yeah. And then when my path led through several stages. At several stages, I first studied aerospace engineering originally, and then I realized I was more attracted to more the mathematically oriented aspects of engineering. So then I studied systems and control, which is a very generic field of study, actually, because you learn to control systems kind of independently from what kind of system it is specifically, right? It could be a machine, like a mechanical machine, or an airplane, or it could be an electrical system, or it could be even something in the environment, like, for example, I don't know, or a hydroelectric dam or something like that. They can all be fundamentally described with the same kinds of equations, and you learn control tools to apply these in a generic way to any kind of system. So when I was done with that, I was looking for PhD position and an interesting thing to do with the tools I've learned in control and control engineering. And at the time, I, by coincidence, heard about nuclear fusion and the fact that there are many control problems to be solved in nuclear fusion. So I found that very attractive to merge my interest in control, to combine my interest in control with doing something, you know, which would be good for against climate change and good for the environment on the long term, and also be a really challenging, interesting technical challenge as well. So then, yeah, then I did my PhD, and then things kind of continued from there.
I appreciate all the detail in your answer. Thank you. And I know you haven't been here before. I see your party hat. So again, welcome to Science Society and welcome to Clubhouse. But what I'd like to share with you is that from asking the different guest researchers, I'm seeing this thread of the desire to problem solve and then using the education to find the tools to do that, whatever the curiosity is that that is motivating you. And you've done such a fabulous job of answering the question that you led straight into my second question, which would have been to ask you, what was the path that led you to your research today? And you have already brought us there. So thank you so much. At this point, the mic will be yours, and you're welcome to begin your talk and tell us about your work. And then afterward, it's our tradition to have a Q&A, if that's okay with you. Some guests prefer to have the Q&A as they're speaking, and it's totally up to you. But the mic is yours, and you're welcome to begin. Thank you so much.
Okay, thank you very much. Yeah, as so yeah, this is the first time for me actually speaking in this clubhouse, so I have to get used to the format as well. But yeah, I just start speaking about it and didn't really prepare a presentation. I'm just going to speak about the work and then refer to some particular figures for some parts of it, which are listed, which are on the actual paper, which you can find online, and I think was also shared in this group or in this room. I think it's called like that. And for the questions, yeah, of course the Q&A at the end is fine. And also if during the talk there's like some kind of urgent question, it's fine to interrupt. I might just not always be looking at the screen. I might not always be looking at the phone. So if it's important and it's in the chat, for example, then somebody might just speak up. So if that's all okay, I'll just get going.
Yes, if I may just let you know that
Yep.
it's our intention that you can relax in here, and it's up to us to do any moderating. So
Okay.
we will handle things such as questions, and if there's also anything, for example, if you think of a link that you'd like to share, if you just mention it, then any of us will be happy to share it in the chat. And as you can see, the link to your work is above, so you can refer to all of the slides. So we've got you covered.
All
Relax
right.
and
Thank you.
enjoy.
Fantastic.
Yes, and yeah, when we do bring friends up, then please flash your mics and let us call on you so that we can establish an order of offering the questions to our guest, and that would really help with the room flow. So thank you so much, and I pass the mic back to you.
All right. Thank you. So first of all, let me just give a brief introduction to fusion and what it is we're trying to achieve with this research, and also what the actual status is of fusion research right now, right? Because that is kind of the context within which all of this work took place. So fusion, fundamentally, nuclear fusion is the process that powers, for example, stars, that powers all the stars in the universe by fusing hydrogen atoms, which are very small and very light, into heavier atoms. And basically, research on nuclear fusion on Earth is mostly about being able to replicate those kind of conditions in which atoms, light atoms, can fuse into heavier ones, to replicate these kind of conditions on Earth. Now, the problem is that it's incredibly hard to do. In the sun, it works because the sun is so massive that due to its gravity, it has an enormous pressure in its core, and that's why this fusion can take place. But if you want to do the same thing on Earth, this is difficult to do, in particular because the matter that you have to use for this fusion is actually in a state of matter called the plasma. And when something is in the state of plasma, it means that the ions and electrons are dissociated from each other. So you have ions and electrons freely flying around instead of being, bound to the atoms being, combination of ions and electrons being bound to each other. So in a plasma, everything is so hot that the electrons and ions just fly around. So a way we found to try to keep these ions and electrons together long enough and to high enough pressures so that the fusion process can occur is by confining it by magnetic fields. So because the plasma is electrically, the plasma particles are electrically charged, ions are positive and electrons are negative. This means that by using magnetic fields, we can hold this plasma together and increase its pressure for long enough that the fusion process can actually occur. Now, this in theory has been understood since the 1950s and 60s, and since then, the research has been about creating a device on Earth in a laboratory, which can actually make these plasmas, which go to such a high temperature and such a high pressure, and keep the plasma confined long enough that the fusion conditions can occur. Now, you can imagine that there's a kind of balance between all the power you need to put into the device to actually heat first the gas and then make it into a plasma and heat it to these extreme temperatures. We're talking about 100 million degrees on Earth for what we need, 100 million degrees. That's really extreme temperatures, of course. And you need power to get to these temperatures. And at some point, if the conditions are right, you start to get power back because the fusion reactions are happening. So at some point, if you reach high enough pressures, then you can get the power from the fusion reactions. And then eventually the goal is to heat up water and then drive some kind of turbine and make electricity in the same way as you would in any other regular power plant like that we have today. So the goal is to make these kind of machines work, and there have been various attempts at making machines with configurations of magnetic fields to confine these plasmas. Now, it would take too far to actually go and discuss all these in detail, but one particular one which has been quite successful is the so-called tokamak configuration. And in the tokamak, if you look at the actual paper and you open figure number 1, which is on page, I guess 2, depending on how you're looking, it's on figure number 1. If you look at figure G, you see what the tokamak actually looks like. So you see there's a combination of various these things that you see going around are like these electrical coils which carry electricity, and they are used to create the plasma to confine the magnetic so they're used to make the magnetic fields to confine this plasma. And the actual plasma is the thing you see in the core, the thing in yellow, which is then held in place by these magnetic fields created by these magnetic coils. So the trick of a tokamak is to actually make the system axisymmetric. So you see in this figure, it's axisymmetric, meaning it's shaped like a torus. So it's like the magnetic field lines are closed on each other because of this donut-like shape of the magnetic field. Now, in principle, this all works fine, and people have been studying tokamaks already since the 1960s, and we have been able to make increasingly high temperatures and increasingly high pressures in these systems, in these tokamaks. So, and what we found out is that by making tokamaks bigger and bigger and putting more and more power into them, we can reach closer and closer to the conditions where it actually becomes profitable from an energy point of view to actually make the plasma, and you get more energy out or more power coming out than what you're putting into them. So, so this research has been ongoing for many years, and actually now we're at the stage where the construction is underway of the world's biggest tokamak, which should be the first to generate more power than you are putting in, which is called ITER. If you want, you can look it up on iter.org. So iter.org is the website which explains this incredible construction site, which is now ITER, this incredible project where there's many countries participating. Almost all the world is participating in this big scientific endeavor to make this gigantic tokamak, which should be the first where there's more power coming out of the plasma with respect to what you're putting in. So this is just to give you an idea of a flavor of what nuclear fusion research looks like right now. And I should say, it's a very, it's a research field that's very active, and there are many researchers across various research communities in many different countries working all together on this problem, both from the engineering point of view and from the, let's say, more, the engineering point of view to actually construct and to design these tokamaks, and from the physics point of view to try to understand fundamentally how these tokamaks work and how these plasmas work, so that we can improve how they behave and control the plasma to as high as possible pressures, for example. So then specifically about the work that we did here, as I mentioned, one of the issues with having one of these, having a tokamak, is that you need control to actually keep your tokamak plasma where it is. So in order to control, to make sure that the plasma stays there, you have to actively feedback control it, which means that you have to take measurements in real time about what is happening in the tokamak. For example, you have to measure locally the magnetic field and a number of other interesting quantities. You need to measure these in real time and then feed this to some computer, which very quickly, 10,000 times per second in our case, needs to decide what to do in terms of how to control the coils used to generate the magnetic fields to confine the plasma, how to control these coils. So every 10,000 times per second, the computer has to make a decision about what to do. And not only, and increasing other extra problem with this is that the actual position of the plasma is unstable. This means that if you don't do anything, the plasma will just by itself fly away and go against the wall, for example. Now, in the majority of the tokamaks that exist today, this is not a huge problem, because the walls are made of a material which can actually withstand this without any issues. But in the future devices we want to make, this may be more problematic. I would like to say, not from the point of view of like human safety and these sorts of things. I should say nuclear fusion, for a number of reasons which I can't go into today, is much more safe than the nuclear fission reactors that we have today. So there's no risk of like catastrophic meltdowns and things like that. But it might be that if you're not careful and your plasma becomes unstable, it might be that it could, for example, damage the reactors, and then you have to repair it, which of course is a bit, so it's something that you want to try to avoid, of course. So this control is really, really important to do. It's actually absolutely essential to do this control. This is why for many years, since the first days of tokamak research, people have understood how to do this and have tackled this problem using traditional control engineering techniques. So I told you earlier, I started originally as a control engineer. So in engineering, there's all sorts of fantastic techniques to do design of control systems, starting from the mathematical description of the system that you're trying to control. So you can do that for a tokamak as well. For the tokamak, you can write down the equations which explain how this tokamak plasma is going to move depending on what you do with these control coils. It is really quite literally, as you see in this, again, in this figure 1G, you have all these control coils, like these yellow ones, for example, and if you increase or decrease the current in one of these coils, the plasma will move to the left or to the right, for example. So the way this has been tackled with original control engineering approaches is to describe this using a mathematical model. And then, with this mathematical model, there's control engineering techniques to derive what kind of, how you can design a controller for your tokamak. So the controller, for example, so the traditional way it's been done is you can actually see it in figure 1D. If you look at the part where it says, F, where it says conventional control. So in conventional control, you would actually split the problem into different pieces. You could, for example, say, let's first control the position of the plasma in the vertical direction and in the radial direction, for example. And then you make a specific controller for that, and they have to be independent somehow. And then you make another controller for the total current in the plasma. That's another quantity we need to control. And then you make another part of the control for the so-called plasma shape, which is basically when we say the plasma shape, we mean, if you look again now at figure 1H, where it says vessel cross section, you can see this plasma has a kind of a shape, which is this black curve, which is going around the plasma, and there's an X somewhere, and you see the plasma has a particular shape, right? It's not quite circular, it's slightly, it's a slight elongation, how we call this. And so this plasma shape is something you want to control, because this plasma shape has also important effects on how good the plasma is going to be at magnetic confinement, at confining your, at getting high pressures, for example. So the traditional way is to do this, again, separating the problem into various individual control loops and then trying to control these all at the same time in some way by basically by tuning the control parameters, first using a mathematical model, and then by tuning them empirically. Often on your tokamak, you try an experiment, you try to make one of these plasmas, it doesn't work, and then you tune, you change your control gains, how we call them, we change these gains in a way until it works. So this was the starting point of our research, is that these kind of techniques already exist and they're very successful, and many tokamaks around the world work every day and create all the plasmas they want with these kind of existing control techniques. But so what we try to do is to try to find an easier way or an alternative way to design these controllers. So I mentioned in the traditional techniques, you're relying on a mathematical model. You have to make specific assumptions to derive this model. And also, as I said, it's quite tedious in some ways to have to tune all of these control gains, because there might be like 20 different parameters and you need to tune them all because they all have an effect on how your plasma is behaving and how your plasma control is actually working. So what we try to do is to try to solve the whole problem in one go. So at the same time, try to do everything to control all the quantities at the same time, and also try to, go directly from the magnetic measurements. So from the measurements of what's happening inside the tokamak, go directly to the control. So directly say, this is what the different control coils should do. So that's shown actually in figure 1E. So you see, as opposed to the conventional control with the various different blocks and various different loops that you have to tune, just to make one single, what we call a control policy. So that's just one single block, if you want, which will do all of the control. So that's what we try to do. And in particular, we try to design this using a technique called reinforcement learning. So this is where it's really important to remember that this work was done, as I said, by EPFL, which is my university, where we have the TCV tokamak, which is, again, a tokamak that we use for scientific research to study these kind of things, including control problems. And for this work, we collaborated with the group at DeepMind, which some of you may know. DeepMind is a research part of basically of Google, and they do research on artificial intelligence, in particular on reinforcement learning. So ours was a collaboration with them, where they have all these tools to solve control problems using reinforcement learning. And so we worked together to apply these techniques on the tokamak control problem. Now, I'll very briefly explain what reinforcement learning is. So reinforcement learning is a technique in the field of artificial intelligence, which is a way to try to get computers to learn things in a similar way as human beings learn things, by interacting with the environment, which means they just try things out, like a child would try things out, interacting with the toys in his or her environment, in their environment, to interact with these toys and try to figure out, how to get the outcome that they are looking for. So reinforcement learning is trying to do the same thing, but trying to make computers learn in the same way. So what we did in this specific case is to apply reinforcement learning to learn how to control a tokamak by interacting with a simulation of the tokamak. This had two parts. One needed to actually have a good simulation, which describes accurately how the tokamak behaves, meaning what actually happens in the tokamak when I put certain currents in certain coils, what kind of plasma behavior do I expect, and what kind of measurements do I expect to see, right? So this is really where all the physics knowledge and the engineering knowledge has to go in to make models of sufficient quality that they can really represent how the tokamak plasma is going to evolve as a function of time and as a function of all of these inputs that you're putting in. So once we have this mathematical model, then we apply reinforcement learning, which means basically that you are having your computer controller interact with the simulation many times. So basically the controller is trying out different things. At the beginning, it will fail. It will not do the correct thing. And then it gets a bad score. Basically, that's the idea. And then when it accidentally does something good, then it gets a higher score. For example, if it maintains the plasma stable and successfully maintains the plasma inside the reactor for a long time, it will get a good score. And if the plasma becomes unstable and ends up in the wall, it gets a bad score. So then by using this, there's all sorts of very sophisticated algorithms to then actually get your reinforcement learning to work. So to learn what control should be done. So how it should be, how the control system should act, and how the controller should behave. And yeah, so this was really interesting to see that you can do this already just in the simulation. So already just by being able to just learn by interacting with the simulation, learn how to control a tokamak plasma. This is already very interesting thing that just works. But then the next step we took was even more interesting. We actually took the controller that we had learned from the simulation and actually applied that to the actual control of the real tokamak. So we took the controller which was learned using reinforcement learning, and we applied that to our tokamak here, the TCV tokamak at EPFL, at the Swiss Plasma Center. And we saw after there was still a little bit of trial and error that I might tell you more about in a second, but relatively quickly we got this to work, and we really saw that it worked the way we had expected. So the plasma was indeed maintained in a proper way as we had expected. Now, what is the advantage of doing things like this compared to the original control engineering techniques? So as I mentioned, one advantage is that you don't have to tune these individual gains. It solves everything in one go by trial and error, and you get one big controller out which does everything. Now, another advantage is that you're very flexible in how you specify what you actually want, in the sense of how do I want my plasma to actually look. So like what kind of plasma shape do I want? Where do I want this little red X? If you look at the figure 1H. Where do I want this little red X? This can be in many different places. Where do I want it? Well, you can specify where you want it. You can specify which things about your plasma do you find important, and for which things can the control system just choose by itself what to do, right? So for some, you can specify it in a completely different way. If you use the traditional control engineering techniques, you have to exactly say, I want that plasma to be in this position at every moment in time, and I want my shape to be like this at every moment in time. But with these reinforcement learning techniques, because in the end, we only are going to give the thing a score, we can decide how we're going to make this score. So we can put in the score, we can put the things that we actually care about, and the things that we don't care about, we don't need to put into there. So this is really a great advantage because it makes everything much more flexible in terms of how you prepare your controller and how you specify what you want to do. So this is so this is to explain, right, the advantages and the disadvantages. But now, of course, you're probably all interested in actually seeing what this thing can do. So if you go, for example, down to figure number 2, you can say an example, figure number 2 in the paper, fundamental capability demonstration, shows an example of actually controlling the plasma in the tokamak using this particular controller trained using reinforcement learning, so trained using artificial intelligence. And you see the plasma begins, and then at 0.1 seconds, we switch from having, we switched to the machine learning controller, the reinforcement learning controller, and you see that because we had programmed it like this, the plasma first moves to a different location. It starts kind of high up in the vessel, and then it moves kind of to the center, and then it forms this so-called X points, right? Cross that we were speaking about earlier, and then brings it back all the way to the top at some point. So it's really manipulating the currents in the coils to achieve this in real time. So 10,000 times a second is making a decision about what to do. And if we now go to figure 3, you see that we try this on many different configurations, so many different shapes. So we're interested in studying many different shapes in tokamak to see which ones work better or not. And you see, like in figure 3, A, B, C, and D, you see a number of these different shapes that we actually did and that the controller was successfully able to achieve. And we did something else in figure number 4. You see even an example where we used the reinforcement learning controller to do something new, which is to make actually 2 different plasmas at the same time, one at the bottom and one at the top of our tokamak. And this was really something new, which was easy to do with the reinforcement learning because we just had to change this score. We only had to say, now instead of the score being, for example, the position or the X point location or these sorts of things, we just said, make 2 plasmas and put them in this position and have this much electrical current in them. And then the tokamak and then the reinforcement learning controller would take care of this. And we'll just do this by more or less by itself. So this was for us the first time that we could actually control so accurately and for such a long time these 2 separate plasmas in the tokamak at the same time. So with this, I think I can maybe for now conclude this technical part. Maybe I'll say just a few words about where we want this work to actually go to conclude, right? Because now we use reinforcement learning to solve the so-called magnetic control problem, right? What I talked about today was the use of the electrical coils to control the location of where the plasma is. But that's not the only problem we need to solve, of course. And this we could do already since many years. We knew how to control plasmas. We just found a new way, a much more flexible and very interesting way of doing this. Now, in the future, what will be really interesting is to see if we can extend this idea and this concept to actually control more aspects of the plasma. For example, we want the plasma pressure to be very high. We want the confinement time to be very high. So we want to have good plasmas that can make a lot of fusion power in the end. That's what we're all trying to study, and what we're all trying to achieve is to have very high levels of fusion power, because that's what's going to get us our electricity production in the end at some point. So what we would like to do is, for example, to say, well, you know what, just tell the reinforcement learning system just to say, please make the best plasma that you can, where by best we would mean, for example, with the one with the highest pressure or with the highest amount of fusion power, for example. And then the ultimate dream is that we could really ask the machine learning or the artificial intelligence to maybe design an entire fusion reactor for us. If we just say, make the fusion reactor which makes this much power, that has, let's say, maximum this kind of cost, or try to make the cost as small as you can, for example. The ultimate goal is that you would be able to do this, but of course it's much more complicated than what we did right now. The first reason is that you need to add all sorts of physics effects inside the mathematical model that you use to actually, that the reinforcement learning agent has to interact with. This model has to be much more complicated. Now we have only the model for the magnetic control, which is just one part of the whole fusion problem. To have the entire modeling of how an entire tokamak behaves requires you to also model the internal effects of how the pressure increases as a function of how much you heat it. And there's very complicated physics and very sophisticated physics mechanisms going on in there, which are very hard to model. This is a topic of active study by many physicist colleagues, trying to understand how to actually model what happens inside the plasma, what happens to the exterior of the plasma when the plasma enters into contact with the much colder wall, for example. These are all very complicated physics equations which all have to go inside this model to make one single simulator which is so good that then we can use reinforcement learning and just ask the problem, ask the reinforcement learning, please make us the best possible plasma that we can. And then it would design the whole tokamak, put the electrical coils in the place they need to be, put all of the other engineering systems around the plasma in the way they need to be, and then it would design for us the actual first fusion reactor, for example. That's really the ultimate dream. We're very, very far from achieving this dream. But this example of using reinforcement learning for magnetic control is a first step in this direction. So yeah, we're very excited to also to continue this work and see where we can go indeed by bringing, you know, all of the work from the fusion scientists to make the simulation models and understand how plasmas work, bring it together with the computer science aspect and using this powerful technology of artificial intelligence and reinforcement learning, yeah, to also advance fusion science in this way. So that was all I had for today. Thank you for your attention, and I'll be very happy to answer any questions you might have.
I have a very brief one. This is amazing research, by the way. This is so cool. One of the questions I have is will these techniques work with other geometries as well? You've mentioned tokamaks many times, but there's a number of new types of fusion reactor designs everyone's coming up with, like, you know, it seems like on a monthly basis now. Will these same general techniques for AI, for being able to drive some of the design or the operations components, will they also be applicable to some of those designs as well?
Yeah, I expect that they would be. The problem is always going to be how good is your model, and how much space or how much need is there for control. So I should say that indeed reinforcement learning is particularly good at actually learning control for so-called dynamical systems, so systems that evolve as a function of time and that need this kind of control. But in the broader spectrum of artificial intelligence, there's all sorts of methods to solve optimization problems. And indeed, I do think that machine learning and artificial intelligence, in a general way, can be used for optimization of many other fusion concepts. There are a few indeed. One of the main issues is that, you know, there are always like fundamental physics laws and fundamental physics reasons why a particular configuration might or might not work. But indeed, you can use artificial intelligence if you have sufficient understanding of the underlying physics, that you can put the physics into a computer, using having a computer model, and then using AI to interact with this physics to design the optimal reactor for that particular configuration. So absolutely, I think it can be done, but for many approaches, the bottleneck is actually getting the physics models well understood enough and being able to put them in a computer. That's, or also for tokamaks, that's incredibly hard to do. So
Excellent.
that will be that will be really the bottleneck in many situations. I should say also that, you know, artificial intelligence is being used all around the world for many applications, many different engineering applications for further optimization, exploring alternative configuration, you know, also in all sorts of other engineering systems like planes or ships, or I don't know. And in this sense, fusion is no different, exception being that really the physics and the models of fusion are very, very hard compared to some of these other systems.
Very, very cool.
Hello, Dr. Federico. Thank you so much. It's wonderful to hear. I have a couple of questions, and you already answered the one about the simulation in terms of how it's so dependent, like on the act of research to get that simulation right. How many points of data then? I mean, so the assumption one is that the simulation has to be correct, right? And the physics is correct, based on the kind of variables that you're going to use. How many kind of training points then does it take for then the AI to learn? Like, how many points of data using the simulation does it take?
Yeah,
Like,
that's hard to actually quantify. If you think about, so what it typically did is to run, for example, one simulation, let's say, would be like simulating the stabilization of the plasma for 1 second. Okay, for technical reasons in our TCV tokamak we can confine plasma for at most 2 to 2.5 seconds. But just to shorten the experiment, we said, okay, let's try to, typically we try to do a simulation of stabilizing the plasma for 1 second. Then to do that, you need to do a simulation which actually runs, I said the control runs at 10,000 times per second, but the actual simulation runs at 50,000 times per second. And every 50,000 times per second, you get one data point, which would be like, all of the magnetic measurements, which are about 100 of them. So you have 50,000 times per simulation. You have these 100 numbers, which are the values of these magnetic measurements at that particular time. Now, let's say you have one simulation, which means that the controller will attempt to do a particular thing during that one simulation. And then to get reinforcement learning to work, you need to do many of these simulations. I honestly wouldn't know what the number is. It's in the many thousands, probably more. So yeah, so you need to run these things on relatively complicated computers, also because the simulation is actually relatively slow to do. So you need a lot of computation power to do this. And I wouldn't even be able to tell you actually how many individual trials it had to run, but it's many, very many.
It's
in
pretty cool
terms of
because some of the
time,
check on.
sorry, in terms of time, like how long would it take to like do one kind of
Yeah,
training
so
set?
it depended a bit on like how many attempts you're doing in parallel and how hard the thing is that you try to do. Let's say for very simple cases, and say you're doing 20 cases in 20, you're trying it with 20 controllers in parallel, it looked like a couple of days. And if for the more complicated cases, they had to use many more of these so-called many more of these trainings in parallel. If they did maybe for more complicated cases, it was about 5,000 things are being done in parallel, and that took like a couple of weeks. So you can imagine this still takes significant computational power. Now, there's many ways to improve this, and some of these we mentioned in our paper, and we want to work on in the future. One of them is, of course, to accelerate the actual simulator. So if you get the simulator to work more quickly, then of course this reduces everything, and that's more in the in the realm of numerical mathematics and improving the from the computational point of view, improving this. The other is to be able to have algorithms, reinforcement learning algorithms, which need less data to learn, so use the data that they have in a more efficient way, and that's also an active area of research, more on the reinforcement learning end.
You mean the
Yeah.
optimization? You mean the optimization aspect of it? Oh, and the other thing, so there's a couple more questions to follow, if that's
Yeah.
okay. And so, and then, right, so it's interesting to learn about how much training time is required, and then the scoring, right? So, in terms of the target, how is that then defined? I mean, like, I'm guessing there's a black box, right, to get to, but then how do you even determine what the target is? Like, the stabilization of it, like how do you determine the stabilization of the plasma? Is that right? Like how do you score it?
So now there are many ways to score it. I'll start just with the very easy, very simplest one, which is the first one that we did. So there's 3 basic quantities that you always need to control to even have your tokamak plasma for any interesting length of time. So those are the vertical position, the radial position, and the total plasma current. So these 3 things. So the first thing we did is just to try to get the reinforcement learning agent to learn these 3, which just means we just specify, make the Z position, the vertical position, be equal to this, the radial position be equal to that, and the plasma current value equal to this. So we specify references, or we specify targets for all 3. And then the score is simply how far you are away from these things, from these quantities, from these references. And of course, because this evolves during time, right? You want to do this for 1 second. The score would be something like cumulatively, how long have you been, how far away from these targets, and the further you've been away, the lower is your score. So the smaller you make the error, the higher your score. That is the most basic, simple thing. Then you have more complicated things when we actually want to, for example, control the plasma shape or the X points. Then we specify some deviation with respect to your references, with respect to your targets in a different way. For example, I talked about these X points, these little red crosses in the figure, and we just specify where we want these X points to be. For example, if that's something that you really care about, you put that in your score. If you don't necessarily care about where your X point is, then you don't need to put it in the score, and then the algorithm might find something else to do, which is more optimal in some other way. But for example, if you look at figure 2, you see these blue dots, and these blue dots which are kind of surrounding the plasma contour. This is the goal. So the reward would be keep your plasma boundary as close as possible to these blue dots, right? This is the reference is trying to achieve, and you see, they're almost on top of the black curve because the controller is doing such a good job.
It's
That's basically the story. I hope that answers your question.
It's pretty cool that when you described earlier about the time sequence on being able to break down the problem to, you have 2 seconds and you have 80,000 or 100,000 different discrete moments that you can break that into. It reminds me of some of the other things that DeepMind has tackled earlier, where the team was looking at like StarCraft playing, and for them there you have like 100 actions per minute or something like that. And typical game will be like 20 minutes or so, but discretely when you add it all up, it ends up being about 80,000 or 100,000 different discrete moments in the overall state of the game and how they can optimize it. I'm not sure if they're using the exact approach of the same things, but it's interesting seeing the general philosophy applied there.
Yeah, absolutely. Yeah, that's an important aspect. So of course, while StarCraft is completely different from nuclear fusion, they both are, in a sense, they both can be treated in kind of the same framework. That's the interesting thing, right? It's an environment. Your controller or your agent has to interact with this environment, and there is dynamics in the sense that what you do right now might have an effect in some future. Right, the decision you make at a certain moment in StarCraft to do something has an effect in maybe 10 seconds or in 1 minute or in 2 minutes or 10 minutes into the game. And similarly, if you try to change the current in one of the coils, this will take some time before the current is actually changed. It doesn't happen instantaneously, and then as a function of time, the plasma is going to move and it's going to interact with all the other coils, and many other things are going to happen. So that's where the dynamics of the system is coming in. Now, an important difference is that, of course, in StarCraft, we should say that the understanding, let's say the StarCraft is, or any other kind of game, there's no difference between the simulation and the actual thing. You're only interacting with something that exists in a computer. So there's no issue with having to learn something in a simulation and then transferring it to something else, which is the actual hardware, the actual system. So I should say, from the reinforcement learning point of view, using reinforcement learning to tackle these kinds of problems, so a real engineering problem, a control problem on a real engineering system with this many inputs and outputs and with these kind of speeds, so 10,000 actions per second, is also new and also really pushing the frontier of what can be done with reinforcement learning.
Dr. Frederica, thank you so much for your amazing presentation. It's really interesting to see all of the figures and being able to visualize the plasma flows and things of these nature. I've definitely heard magnetic constrictors uttered by Geordie LaForge on Next Generation more than once. So it's it's really interesting to see that parallel. So I was curious about you said there was a scaled up version of one of these tokamak reactors in progress. I was wondering what the ETA on that was and the cost, and then I have several other questions.
Yeah. So first of all, thank you for making this parallel to Star Trek. I do also tend to make these kind of parallels occasionally in my day-to-day work. Not always appreciated in the same way by my colleagues, but that's what it is. The way, yeah, speaking about ITER, it's so ITER is this new tokamak that's under construction. It's it's a very big science project. It's really one of the most complicated science projects that as humanity we have ever attempted. I wouldn't be able to tell you actually the exact cost, but it's in the tens of billions. And the ETA is currently to have the first plasma. I don't even know the official schedule at this point, but like certainly within the next five years. So it's well on track to finishing the construction. My understanding is that it's now 75% complete. I think if you go on iter.org, you'll find all the information and all the status of the construction. And I mean, they're really at the stage now where they're starting to really assemble all of the different components. But just to stress, it's really a big science project, an incredibly complex machine that we're trying to make. Just to frame this even more, the magnetic coils that we use on TCV. So TCV has a size of like the whole thing is maybe 2.5 meters across. Let's say the whole device is approximately 2.5 meters across. ITER is like 25 meters across, so it's much bigger. And the magnetic coils that we use are made out of copper, right, which is kind of easy to deal with. The coils in ITER, for various reasons, particularly to keep the plasmas confined for a long time, ITER will aim to confine it for 300 seconds. That needs your coils to be superconducting, which means that the coils have to be inside the cryostat and have to be cooled to very low temperatures to put the magnets in a superconducting state. So you have somewhere superconducting magnets at very low temperature, and then just a few meters from there, you'll have this incredibly high temperature burning plasma at 100 million degrees. So the engineering challenges of that are just mind blowing, as you understand, and there's of course also the associated cost.
So I can assume the why it's called ether, but it's linked to like the actual stuff.
Jamie, you had a question?
Sorry, I
I'm
didn't
sorry
hear the
about that. I
question.
was
I think it
fixing.
was
Sorry, I was
that.
wrestling with the mute button there. Sorry about that. Thank you very much for this talk, Doctor. It's absolutely fascinating. And I'm going to ask a kind of basic question. So forgive me if it's a bit simple, but I was wondering when you were talking about the different shapes of the plasma, like the snowflake configuration and stuff. Why exactly is that like important? Is it because of the complexity of what it takes to control it, or does like a snowflake shape do something that like a elongated one doesn't? I'm a little bit
Yeah.
unsure of that.
No, that's a
Okay.
very good question. And indeed, the detailed reasons are very hard to understand. They have to do with complicated physics phenomena, like why the way the particles in the plasma move around in a given magnetic field, and what happens exactly, and what kind of instabilities occur. So the fundamental reason is indeed hard to understand. Maybe one which is interesting is like why we care about where these X points are, for example, why we care about these X points. And you see like in figure 3b, no, yeah, figure 3b and 3d, for example, you see that there's this number of legs, right? This snowflake, for example, that's number D. So in these, the point is that what happens with these, what happens with these X points and with these legs in particular defines like if some of the heat and some of the particles escape from the plasma, where do they go? So now they tend to preferentially follow the magnetic field, which means that they will follow these legs. And that's a very good and very important thing, because it means that then we can decide where the majority of the flow of the plasma coming out of the device, where it will interact with the reactor wall. And there maybe we can put some cooling, or we can put some other devices and take some other measures to make sure that this heat flux coming out of the plasma is handled in a proper way. So that's one reason why we care about the plasma shape. And really, it's a topic of active research. Like, for example, the number 3C, that's what we call negative triangularity, because it's shaped like a triangle, but the opposite end of what one would normally do, right? B is kind of closer to what you would normally do. So C is negative triangularity, so opposite triangularity. And actually only very recently, this research has gained really lots and lots of new momentum, because people are finding out that this negative triangularity, for complicated reasons, which we partly understand and partly we're still trying to understand, actually has a much better confinement, so can give you a higher pressure than the ones with the D shape in the opposite direction. So it's really a very good question, and the answer is incredibly complex, and I think we also don't know all the answers yet, and that's exactly why in tokamaks like TCV we try to make plasmas in all these different varying shapes, and and to understand what they do.
I think I see. So in experimenting with the shapes, it's essentially experimenting with how much you can control this plasma, which means you can then in future build machines or systems around that to maximize its potential, yeah?
Yeah, it's like that. Well, there's two aspects. One of them is deciding what kind of shape you actually want, which means which shape is optimal, which shapes will give you the highest performance in terms of the highest fusion power, the highest pressure, and so forth. And the other aspect is, even if you design a shape that is optimal, can you actually control it? So can you actually have the successful feedback controllers which will stabilize your plasma in that position? And then actually the third step is to actually then to design these controllers.
That is fascinating. Thank you so much for your talk, and thank you for answering my questions.
Quickly, coming to the top of the hour, I wanted to check in with you, see how much more time you had left.
For me, it's okay. As long as there are questions, I'm happy to stick around.
Perfect.
Fantastic.
But don't leave an open end for us, or you will stay here though, like for 24 hours. But yeah.
Well, let's see. Let's say another. Yeah, let's see. Let's take another half an hour in any case, and then we'll see.
Okay. Thank you so much.
So I have two questions, and then we'll do mic flashing to see whoever else has questions. Please flash your mics now so that we can establish the order. Okay, no mic flashes for now. We can do that again after I'm done. Oh, Jamie, okay. So I was curious about if you had considered, rather than a single chamber for the plasma, several chambers, and also in the experiment where there were two plasma streams, were they of different composition?
Yeah, so first of all, no. So the two ones would not have a different composition. They were kind of the same. Now, having the two different chambers, maybe I should explain. So the fact of having these two separate plasmas is very interesting from the control point of view, but the ultimate goal is to actually bring these plasmas together in a controlled way. That's the ultimate goal. We didn't do this so far. We didn't achieve this with these controllers so far. It's something that we may want to work on more in the future. But yes, actually, in the 1970s, people experimented in the United States, in particular. People experimented extensively with tokamak reactors, which had a shape in which it was easier to have these two plasmas separately and then bring them closer together in some way. This was already studied extensively in the 1970s, to the extent that they could at the time, of course, with all the technology that existed then. And actually, we would be interested to try this again in TCV, to have these two plasmas and bring them slowly together, because we think that there might be some interesting advantages there. So now with more modern control equipment and more modern also equipment to take measurements from the plasma, we are really interested in studying those again.
Related question, is it convenient or is it possible to get something like a stream or a beam coming off the plasma along one of the legs?
Well, you could, and that's in practice, that's what actually happens, in the sense that the pictures you're seeing in the figure, they are highly, let's say, highly idealistic, where all of the plasma is confined within this black thing. In reality, there's all sorts of plasma coming out all the time. Actually, I might just share a link maybe where you can actually see what is happening. Just 1 minute while I look for it. Right, I have a link. Now let's see if I can find out how do I share this.
If you click on the chat button
Yeah,
all the way
here.
left, yeah, there you can share with the room.
Right, I
Yep.
shared it in the chat. That's actually, yeah, that's actually really a really nice picture that one of my my colleagues from EPFL took very recently. Well, he wasn't actually standing behind the camera. Okay, when we actually make the plasmas, nobody can be in the experimental hall, but he. Yeah, we have some camera systems which take pictures of how this plasma inside the TCV tokamak actually looks. And that's the way it actually looks. So you see this vague purple haze that you see around the plasma. You see actually that some of the plasma is exiting somehow, and then some of it is going higher, like it's becoming blue and is ending up interacting with the wall at some point. So this is what the way an actual plasma looks. And the reason it has different colors is because depending on the various temperatures that exist in various places in the reactor, and depending on, for example, what kind of materials are there, you can get completely different colors and see different things. Maybe another interesting thing to point out in this figure is that you can't actually see the plasma core, because the core of the plasma, which is the hottest and has the highest density, is so hot that it doesn't emit any light in the visible spectrum. So a normal camera cannot see it. It's emitting mostly in the X-ray frequencies, let's say. So then we have lots of X-ray cameras which actually are able to see these, and then we can tell interesting things and see interesting things about what is happening inside the plasma. But you have to really look at it in the X-ray spectrum to see anything. I hope everybody can see the link. If you haven't clicked yet, I highly recommend you do, because it's really a really fantastic picture to bring it kind of from the kind of conceptual schematic drawings that we show in the actual paper, to see how one of these things actually looks.
Thank you so much. I'd like to do a quick room reset and welcome all the friends who are here joining us to listen to Dr. Felici discussing his work in nuclear fusion and the tokamak configuration. We're grateful, Doctor, that you are giving us another 28 minutes of your time. We were really so looking forward to this time with you. So if anyone has a question, and that you would like to ask, then please flash your mics so that we can help make sure that everyone who's on stage is able to ask a question. And welcome to new friends, Eli, Brian, and Eric, and Dr. Shaw, who have just come up. So who would like to go next? And let's see a mic flash. All right.
Well, I'd like to thank Federica for that answer and ask a follow-up. From what you know about this, is there any way to selectively bleed off specific ranges of particle energies from the plasmas? Say in those legs.
So maybe could you say, like, what kind of applications are you thinking of? Like, why would you want to do that?
Well,
Because in principle, the idea is to try to keep as much of the plasma confined as you can, because we want the fusion plasma to be as hot as we possibly can. So ideally, we wouldn't want to leak anything. Something unavoidably leaks, and then usually we want to leak as little as we can, because whatever we leak, we need to then deal with it by having materials on the floor of the reactor, for example, that can actually stand this, or to have like cooling to actually cool the material wall, for example.
Yeah, so I was thinking about this more kind of as a reservoir for plasma for a reactor that's in a different vessel colliding beam.
Like that. I suspect for like no, I no in yeah, I think I understand what you're saying. I mean, typically it's incredibly hard to do what to like make your fusion plasma even as hot as you can. Sorry, just to understand, are you thinking about colliding beams to achieve nuclear fusion, or are you thinking of
Yeah,
something completely
yeah,
different? Okay, maybe speaking of beams that collide, it's actually been understood for a long time, and in the physics classes when you start your PhD in nuclear fusion, they explain that actually for very well understood reasons it's not possible to make nuclear fusion just by having plasma particles collide with each other head on. I mean, you are going to have some amounts of nuclear fusion, some fusion reactions will occur, but the energy that you would lose just because of all the other things happening, all the other just various collisions between the ions which don't necessarily produce any kind of nuclear fusion reactor will always be higher, and they don't produce a nuclear fusion reaction, pardon me. They will also, this loss will always be higher than whatever you would gain from fusion reaction. So indeed, when they began with nuclear fusion, they studied like if you have two beams of plasma and you make them hit each other, would you achieve nuclear fusion? And the answer is unfortunately no. Otherwise, we wouldn't be still trying this research for since the 1960s. And no, we find that really the only way to do this is to have, at least in the magnetic confinement world, what we understand is the only way to do this is to do this in a so-called thermal plasma. A thermal plasma means that all of the particles are kind of moving around in more or less random random directions, and basically the average of their speeds, of their velocities, is what is this high temperature. That's the way to see it. So they all need to be moving around in many different directions, and the vast majority of the time when they are close to actually colliding with each other, they are not going to make an actual fusion reaction. This happens very rarely, which is why you need this plasma to be around for a sufficiently long time, and all the particles to have many opportunities to collide with each other many times, many occasions, so that once in a while you may get one fusion reaction out of this. And then there's billions and hundreds and billions of of these particles. So then in the end, the number of fusion reactions that you get is very high, and then you get the net positive energy. So I hope that answers your question and gives a bit more perspective on why we want to do nuclear fusion in this particular way.
yes, thanks.
Hey, Jake, go ahead. Please go ahead with your questions, and Armish, Al, and Hansen. Thank you for coming.
Thank you. My question is the chamber shape. Is the chamber shape a variable? Does the AI take the chamber shape into consideration, and can it suggest different chamber shapes?
Yeah, so with the work we did right now, we took the chamber shape of the TCV tokamak, and we took all of the magnetic coil positions from the TCV tokamak, because that's the one we were going to try the experiment on. So far, no. But indeed, one of the potential future applications of this might be to also use AI to, at the same time, optimize this vessel shape, and not only the vessel shape, also the location of the coils and all sorts of other engineering systems you need to put around the tokamak to also optimize this at the same time as the control. But this we haven't done yet. So in the cases you saw now, the vessel and the TCV, the configuration of the tokamak was fixed.
That's awesome. Thanks. And just one other question. How do you know when a fusion reaction has started?
Well, it's actually, first of all, fusion reactions are happening the whole time, even in a relatively small device like TCV. fusion reactions happen all the time, and the easiest way to measure this is by looking at looking for neutrons. So each fusion reaction, in particular in the TCV tokamak, I won't go into details, but in the TCV tokamak, the fusion reaction is between two atoms of deuterium, typically, sorry, two ions of deuterium, and then the fusion reaction creates one new neutron, amongst other things. It creates one neutron, which is not electrically charged, so it just escapes the magnetic field, and it goes, because it's so highly energetic, it just goes straight through everything, straight through the walls of the reactor, and then you can put a neutron detector there, and you can actually measure this. So we do have neutron detectors also in the TCV tokamak, and we measure every day what these neutrons are. So we know that fusion reactions are always going on. As I said, this is a matter of statistics. So the ions and electrons are just floating around all the time. They're colliding with each other all the time, and occasionally one of these, a few of these collisions. Well, a few. I mean, we're still talking like billions and billions of fusion reactions every second in a small device like the TCV. But still, we see that this is by far not enough to actually get more power from these fusion reactions. So these neutrons coming out by far don't have the same amount of power as the power that we had to put into the tokamak to actually heat the plasma to these kind of temperatures. So it's rather a question of getting your plasma conditions with higher pressure and higher confinement time, so that the number of fusion reactions per second increases even more, and then you until you get to the point where you get a net positive energy. Maybe one more point related to this is that actually just a couple of weeks ago, also around early February, there was a big announcement of a new new exciting result from the existing biggest tokamak in the world, which is called JET. It's in the UK, and this tokamak, which is a lot bigger also than TCV, maybe something like 10 meters across for the whole thing. That is, then they saw that they actually broke the world record of how much fusion energy they were able to actually produce during one day discharge. They broke the world record. I don't remember by heart the actual number, but they maintained a significant amount of fusion reactions for, I think, 5 seconds, which is very significant, and within the technical capabilities of what that tokamak can do, it's a very very impressive achievement. And indeed, there the amount of fusion reactions is primarily measured by measuring the neutrons. So if you're interested in that, absolutely go look it up. It's really fascinating. It's really let's say the cutting edge of what we can do in the reactors that we have now, that we have today. If you look it up, so it's the JET tokamak in Oxford, and it's a European tokamak, and that just achieved the world record. If you look it up on Google, you should be able to find all sorts of information about that too.
That's great. Thanks.
Please flash your mic so we can see who else has a question. And all right, great. I see Arnish has a question. Go ahead.
Yeah,
Or
thank you. Federico, my question is, what's the reward function they used in the reinforcement learning AI in the chamber? And is it just maximizing the number of throughputs, number of fusion reaction per cubic, or let's say per unit of two atoms? And the second question is, the output which you would have gotten, the set of settings which you have gotten for a nuclear reactor, can it also be varied in a way that a small level, a small or local level fusion can also happen? Because if you have a simulation result for high throughput, you can also have a controlled low throughput condition, so that even with less resources, these controlled fusion can happen. Or is there a minimal threshold?
Yeah, so to answer your first question, thank you for your question. To answer the first question, so we only did here the so-called magnetic control. So the goal was not to optimize the amount of fusion reactors. It was only to, let's say, try to keep the plasma exactly where we want it to be. So the goal was, we basically prescribed where do we want our plasma to be in the reactor, and the reward function was related to how far are you from what we are asking or from what we need. And as I said, the new work in the future, we hope, will also focus on asking exactly the question you're saying. So to try to get the reward function just to be maximize the amount of fusion reactions, and then give the controller freedom as to how to achieve this. And unfortunately, the problem is that we need to, for that, we need to have actually a higher accuracy simulator, which also includes the effect of the internal dynamics of the internal plasma pressure, the simulation of the amount of fusion reactions, for example, and which is in the current model that we use is not there. There exists in the fusion community, there exist models which can do this. So there exist models which can simulate how many fusion reactions you have. So indeed, we look forward to also trying these kind of approaches directly on controlling the fusion reaction rate, for example. To answer your second question, so yeah, we would all like to have tokamaks that are really, really small, and to make fusion reactors that are really small. Unfortunately, what we understand of the physics tells us that that's just not something that works. We've understood that the way to make tokamaks work, in the sense that to make them make more power than they you have to put in, so to make them work as actual electricity producing power plants, we need to either make them bigger or increase the value of the magnetic field, increase the strength of the magnetic field, which increases the strength of this magnetic cage, so that you can get a higher plasma pressure for the same size. Now, this we have understood for a long time. So indeed, there are two different approaches or two different avenues you can go. One of them is to try to increase the magnetic field, which means using more advanced superconducting magnets, and the other is to try to increase the size. So both of these things are being explored, and ITER, in the sense, is both an increase in the magnetic field compared to the most existing devices. Some already had stronger fields, but compared to many devices, it's a step up in magnetic field, and it's a big step up in size. There are other avenues and other organizations trying to instead make fusion reactors relatively small and increase the magnetic field. But by small, I still mean, it's very significant engineering equipment of the orders of, I don't think there's any design of a fusion reactors which is less than, let's say, 10 meters or so, probably more, between 10 and 20 or something, if you're lucky. And so so this is just from the fundamental. There's a fundamental reason for this in tokamaks, which you kind of understand, but maybe the easiest way to understand it is if you imagine that, when you want to get fusion reactions, what matters is the plasma volume, right? And the plasma volume scales with the size of the device to the power 3, more or less. I'm simplifying things. Now, while what you care about in terms of how much energy you would lose, this depends on the surface of the device, and the surface scales like the size squared. So you can see that the ratio between how many fusion reactions you're going to produce, which goes like r cubed, and the losses you're going to have, which goes like r squared, how that ratio becomes more favorable if r becomes bigger, so if the size of the device becomes bigger. So that's fundamentally one of the reasons. That's not the only reason. There's many more fundamental physics reasons, which I won't have the time to explain today. But we already know that, your pocket-sized tokamak, or a tokamak that can fit in your car or in the truck is just not something we can do. I know that some people have tried to explore also completely other concepts to really make small fusion, much smaller fusion reactors. But so far as I can see, there's no real credible way to do this. And I would say the most advanced and most credible solutions, meaning they have been explored in experiments and they are giving good results on the way towards having a reactor, which gives a positive net energy, are really the magnetic confinement fusion. And then there's two main branches, the tokamaks, which I talked about a lot, and the stellarators, which use three-dimensional magnetic coils to confine the plasma, but they're still magnetic confinement. Yeah, and perhaps, but personally, I think that's a bit of a bigger step is the fusion based on so-called inertial confinement, which means that you fire a whole lot of lasers at a very small ball, basically, of the fusion fuel, and then that basically compresses the fuel very strongly, and you get locally extremely high heat, and that's another way to make fusion reactors happen. Also, these are very, very big. So all these installations are really big, and so far we haven't really found a way to make a viable fusion reactor concept that is small, however much we would like that.
Well, haven't the stellarator designs introduced geometry that makes it more complex? And
Sorry, I have a question regarding the magnets. I don't know if you saw this paper, probably you know, about generating a megatesla magnetic fields by intense laser-driven microtube implosions. That was done in Japan. Um, are you using that technology basically to create these very strong magnets that are comparable to basically a black hole type of force, or are you planning on, like, is this useful? Would this be useful for in your context?
That's an interesting question. I'm personally not familiar with this work. When you speak about mega Tesla magnetic fields, indeed, that's in a completely different world with what we do. We typically have in tokamaks between, let's say, 1 and 10 Tesla, typically, which is already a very strong magnetic field. It's very, very strong compared to the Earth magnetic field, compared to, you know, the little magnets that you can buy to put on your whiteboard. But mega Tesla is something else. I'd never heard of it. But I guess that the actual volume in which these mega Teslas exist is probably very, very, very small.
Yeah, I posted
So
to the paper in the chat if you want to. It's a Nature paper,
okay.
and it says it uses ultra intense laser pulses to produce ultra high magnetic fields.
Yeah. That's interesting.
Yeah, it's probably.
I'll have a look, but I mean, at first sight, I would get that the volumes are very small, so probably it will not be practical in this sense. And also, the issue with fusion is not exclusively to have an incredibly high magnetic field. There are many ways to make maybe even much stronger magnetic field. The problem is you have to maintain this magnetic field for a long time. You have to maintain this over several minutes. To, you know, up to an hour, and possibly even in steady state, possibly even maintain these fields continuously. So I think that will be very hard to do with the kind of techniques that you describe now, and also, of course, the volume of the plasma has to be very significant. So probably if we're talking about these, firing in very intense lasers, is probably for a very short time and in a very small space. But nevertheless, I will have a look at the paper. It's very interesting. Thank you.
Thank you, Federico. I have a quick follow-up. So the trade-off between R square and R cube, did the DeepMind algorithm help you optimize that, or it remained the same in the similar range? So it's more. So my question is it more like an engineering problem, or does AI or reinforcement learning or any technique can help you optimize? Has already.
Yeah.
Oh.
No, I mean, I should say that these things about R squared and R cubed, this is just, you know, very fundamental and well understood just from the basic physics equation, which explain how, you know, how these kind of systems, how these kind of fusion reactors work. And ultimately, even if you have perfect control, you can only do what the actual physics of the reactor will allow you to do. So even if you have the perfect AI and the perfect reinforcement learning controller, there's still, you know, you're still fundamentally limited by what the actual physics is of the system and how much heat loss you're going to have, how many fusion reactions you're going to have. That's not just a matter of good control. It's a matter of can you make the actual conditions inside the reactor which support these kind of high enough pressures and temperatures? And fundamentally, that is, so basically the goal of control is to try to make sure that the only constraint you have is the fundamental physics of the underlying problem, of the underlying equations of how the transport of heat happens and how the heat distributes itself and how the fusion reactors are created. If you do a poor job at control, then you're actually constrained by the fact that, you know, your plasma is not well controlled, it's maybe interacting with the wall too much, it's cooling down too much, and then you're constrained by these engineering things. Now, that being said, there is a lot of space, for example, for AI, to answer a slightly different question, which is, say that I have made my fusion reactors of a given size, and say that I know how much heat, say that I know that in principle it's big enough so that the power you put in is lower than what you are getting out. So in principle, you can get net positive energy, for example. Then you can ask your AI or any optimization algorithm, and maybe AI is one possible solution. You can ask them what is the way I should control my plasma in order for the pressure to be as high as I can. So within all the possible things you could do in that fusion reactor, what is the best way to control it to get the highest possible pressure and the highest possible performance within the constraints of the actual physics. So I hope that clarifies and answers your question.
Yeah, that's absolutely clarifying. And in fact, they can bring a lot of transparencies here. I hope these research by DeepMind is all becomes open source, and people, when they make it transparent, people might get rid of their fear about all of this nuclear energy thing.
So I just gained.
Hansen, Al had a question first. Al, go ahead.
Thank you, and thank you, Doctor, for your time. I had a couple questions. The first one being, once you and DeepMind generated the ML model, can you speak to the computer specifications that were able to run the neural network and manage the feedback control?
Yeah, so that's a very interesting question. So we were severely constrained actually in the computational power that we could use in the real-time control experiment, because again, this has to run at 10,000 times per second, so it's very fast. So there's not a lot of calculations you can do in that amount of time. So the neural network had to be relatively small. It's in the paper, but it's a so-called multi-layer perceptron with 3 layers and up to a couple of hundred neurons, I think, in the actual in this neural network. So this part is relatively easy and relatively simple, and that then ran on a completely standard modern day CPU on one thread. So nothing special, but we wanted it to be small because we wanted to run it on just one CPU. Now, the interesting part, and it's explained in the paper, but I'm happy to explain more here. The interesting part is that the reinforcement learning method that was used is a so-called actor-critic method, and that's a very interesting way of looking at these kind of reinforcement learning problems, because basically the actor is the controller, right? The actor is the one which receives the measurements from the tokamak and acts on the actual electrical coils, while the critic is something else, is a completely different system, which basically is receiving all sorts of extra information from the simulation. For example, the actor can only see the magnetic measurement because that's what it's going to see in real time when it's going to run the control. But when it's learning, it's also only seeing the control. But then the critic is receiving all sorts of other information about, like, the internal state of the simulation, what is the current in the coils, where is the plasma, what does the shape of the plasma look like, all sorts of things which the actor just doesn't know, will never see. So the critic has access to this kind of special information, and then the critic is then basically trying to tell the actor the way it should behave, and is the one that is actually rewarding the actor for doing things correctly or incorrectly. So the point is that this critic, that is a much more complicated thing. That has a dynamical neural network, it has recurrency, it's much bigger and much more complicated than the actor, which was small, and that part is the only one which needed to actually run in real time on the actual machine after the training. Well, in the training itself, we could afford to have this very big neural network but only for the critic part in this actor-critic setup.
Yes, thank you. And also something that I'm seeing from your research is to control the plasma, it seems like it wasn't enough to just maintain a constant magnetic field. Is that because of maybe some unaccounted for anomalies that typically happen within the plasma during reaction?
Yeah, so indeed, one of the issues, well, there's a few different things. So indeed, there are many fundamental reasons why in a tokamak you need to kind of continuously adjust the currents in the coils to make your tokamak plasma stay where you want it to be and to drive the electrical current in particular. There's many reasons, and also because of this, the fact that it's fundamentally an unstable system, you always need to be feedback controlling it. It's like an unstable system is like an inverted pendulum, for example, or like the famous ball on a stick that you're trying to hold straight up. There are always disturbances. So there's always like noise, and there is all sorts of things happening inside the plasma, which slightly perturb the plasma every once in a while. So your feedback controller needs to actively be controlling the coil currents, and they are moving all the time because of that.
Thank you. And my last question is, are there any plans for you to include your research or for your research to be included in the design of ITER?
That's a good question. At this stage, well, not, because the design of ITER is actually fixed. They've already decided how we're going to do it, and ITER, most of the components have already been manufactured, and it's already only in an assembly stage. Now, we do hope that our research will be used to help or assist the design of the reactors, which may be designed and may be constructed in the future. So that's something that, yeah, we're certainly interested in, and I personally hope that there will be a good possibility for this too. But for ITER, things are now fixed, and we already know how it's going to. Because the design is already fixed. Now, that being said, maybe there might still be some space to actually optimize. This linked to the earlier question, to optimize how we actually operate ITER. So how we do the control, what kind of plasmas we want to make, with the control knobs that we have in ITER, in particular related to the heating, for example. When and how do you heat the plasma? When and how do you fuel the plasma? And there is a lot of space for optimization. So optimizing exactly the way we're going to do this. There's already now some pretty good ideas about how we want to operate ITER plasmas, right? That's what the design was based on. But it would be interesting to explore if you can optimize this further using these kind of techniques. Though again, I should say, in the end, we're going to be somehow fundamentally constrained by the actual physics of the device. So a lot of it we will still have to see.
Yes, thank you. I hope to see your research in there as well.
Thank you.
Thank you.
Yeah, hands.
Thank you. Federico, this is fantastic research. I have several questions. Actually, I want to ask this first. Are you going to publish the detailed setup and the mathematical derivations and all the details in a, say, separate paper, or this is it?
Yeah, so this is also linked to the question, sorry, the earlier speaker was asking. So everything we do is basically available, in the sense that the equations of the actual simulator we use are in a document that's actually a PhD thesis of one of our students at EPFL, and that is freely available. So the equations for the simulator are all in there. And of course, this is not something which came out of the blue. Simulators for magnetic confinement simulation have existed for many years and many decades. Even there's many publications explaining all these things in some detail, and also books. And the part about the reinforcement learning control, yeah, it's the specific implementation of how the people at DeepMind actually ran their specific experiments on their computers is not open source, but the fundamental algorithm of how this reinforcement learning was done, what kind of optimization algorithms were used, and all of that theory is available, including all the equations, and including, I think, even an open source implementation of the particular algorithm that was used. So really, from that point of view, we make a maximum effort to make these kind of things available, also to the general public and to others who want to also reproduce our work.
So is there already a reference, or it's in the process?
I'm sorry, I didn't
The
hear. I think the microphone broke. Can you
oh,
repeat the question, please?
can you hear me? Can you hear me now?
Yes, I can now.
Okay. So is the reference already prepared, or I mean, is the ready made reference, or is it in the process of being published? Those detailed
No, all these
accounts.
things I mentioned have already been published, but they're not published in one single place. So there are many references in the paper, and all of the details about, for example, how the simulator works are in one of the references, which is referenced in the paper,
Oh,
and all the
okay.
details of how the reinforcement learning works are also in a reference in the paper. If you want, I can be specific as to where they are. Like, for example, the magnetic the reinforcement learning, or the magnetic controller, the magnetic simulator, for example, is in reference number 22, which is also freely available online if you want to have a look. We don't plan another publication to explain all of the details, because the details already exist. They're all in the references.
Oh, I see. Okay, great. Because I think previously the DeepMind say that when they did the AlphaGo, AlphaZero, they published kind of a different, either as a kind of a very long supplemental information, or another paper, or like the AlphaFold. So
Yeah.
just wondering if yeah. So okay,
No, it's a
so
good question. I mean, in our case, the paper our paper that we have in Nature includes both the main part and also the supplementary material, where a lot of the technical details are. But we don't have any specific plans for a follow-up publication on this particular work.
Okay, cool. So there's another follow-up question is these designs, the neural nets, are they like say convolutional, or the LSTM, or is it say Monte Carlo tree search as in AlphaGo? I suppose that the this is a dynamic kind of a feedback control, and then you have to do it at different time points. So I suppose that these are all in the
Yeah,
supplemental
I also
information,
had to
but
very quickly look it up. Sorry, I had to also look it up quickly in the paper, because I also don't remember all the details. But as I said, the neural network that does the control, so the actor, is a simple multi-layer perceptron with number of inputs equal to number of measurements, so about 100, and then I think 3 layers of 256 outputs. That's the feed-forward multi-layer perceptron. And then the more complicated network used for the critic is mostly based on LSTMs as a first layer, and then whereas one of the layers, and then fed to a multi-layer perceptron. Again,
I
so
see.
that part is more complicated, and that the LSTMs allow, of course, all of the dynamics.
So the critic, isn't that would be just basically solving the Maxwell's equations, and then thermodynamics and or fluid dynamics all combined together. Of course it's nonlinear, but I would think isn't it just solve? I mean, given the control and the or the plasma, and then yeah, and solving these the fusion process, and kind of forward problem. Is that correct?
Well, not exactly, because we don't tell the critic to exactly solve any kind of equation explicitly. What the critic is trying to do in reinforcement learning, and here I hope I don't say anything wrong, because again I'm more of an expert in the fusion control, and I had to learn all the reinforcement learning part much more recently. As I understand it, the main thing that the critic is doing is learn the so-called value function, which just means given the action that I'm going to take now at a given point in time, say assuming knowledge of the system's state, or so let's say given the measurements I have now, and assuming a certain action, what kind of score I'm going to actually get. So the only thing it needs to learn is this kind of mapping between its actions and the expected score. Now, internally, it will probably learn some kind of representation of all the dynamics that's going on in the plasma and how this translates in the end into a score. But this to us is completely obscure. We don't know what is happening. We don't tell it to solve any equations, any physics equation. It's probably not solving any physics equations. It's just learned this mapping. That's all that it needs to do, to learn this mapping as to how well, if I'm in a certain state, if I have given certain measurements and I take a given action, meaning I apply this voltage to the coils, how good is my score in the future going to be? That's all it needs to learn. And that's why it's like this big black box neural network. We don't know exactly how it does it, but somehow apparently it is learning the correct thing because the agent's actions are correct in the end.
Oh, I see.
Thank you so much,
So,
Dr. Felici, and thank you very much for being here again, Hansen. Doctor, I want to respect your time. You told us that you were giving us an extra half hour, and here we are, 40 minutes now. So I want to make sure that friends who have come, I see that we have Eric who's still on stage, and then after that, Doctor, I'd like to let you make your closing statements.
Thank you.
And
Yes.
thank you so much for coming. And friends, please come back again to Science Society. This room is only as special and wonderful as it is because each of you are here. And we feel so grateful that we were able to present a really active and full room and stage for our speaker today. So, Eric, I believe you have a question?
Yeah, so I had a question about the material science, because oftentimes these engineering problems are limited by the technology of their time, and there's been some advances with metamaterials and I guess some other alloys and things like that. Do you see anything coming up on the horizon that might significantly change the geometry or configuration of the physical setup? So you get the tokamak and the stellarator. Perhaps there's another design that could emerge that could combine the two. That's kind of my question. Thanks.
Yeah, thanks for your question. So first of all, I should say, I will try to answer your question, but it's really quite far away from my specific domain, which is really on the control of these tokamak. I'll try to give an answer based on what I know and what I hear from my various colleagues in the field. So indeed, there is a lot of importance and a lot of research going around materials, and there's a number of indeed possibly enabling technologies in the materials field for fusion. One of them, the most obvious one, is everything surrounding high temperature superconducting coils, right? We need to make high magnetic fields, and we need the coils to make them. We need very strong coils that can do this and withstand the strong forces that you get with these high magnetic fields. And we want them to be high temperature superconductors so that we don't have to have such a complicated cryostat. We don't need to cool it to such high temperatures. So everything related to material science for high temperature superconductors is one of the areas where these kind of things can improve, or where material science and physics of superconductors can play an important role. Another one is the everything involving materials in the so-called diverter. The diverter was the area I was talking about earlier, where all the plasma exhaust end up being put, right, where the hot particles from the plasma are interacting with the walls of the reactor, and there's a lot of interest in making high strength materials which are resistant to bombardment by plasmas, and and all of these engineering issues there. And the third very important point is about having materials which are resistant to neutrons, because as I mentioned, the fusion reactions generate neutrons, and these neutrons go through the reactor walls. But occasionally they do interact with some of the structural materials of the reactor, and this may have like long-term consequences for the strength of some of these materials. So there's a lot of active research linked to fusion about making more neutron-resistant materials to be able to, sustain fusion reactions for a longer time and need to do less maintenance on the reactor, for example. And that's also an active field of research, both in the theory field, I believe, and also experimentally to try to test these kinds of materials. Now, as to your second part of the question, if it would enable new things, yes, I think so. Like in many cases, I know for stellarators and for tokamaks for sure, the kind of things you can do, the kind of reactors you can make are just constrained by how you can construct a superconducting coil and by what kind of materials exist to absorb all of the heat in the plasma. These are really engineering constraints which people who design future fusion reactors based either on tokamaks or stellarators have to deal with every day as a strong constraint to their reactor designs. So indeed, having, for example, high temperature superconductors, the advances there have led recently actually to a number of new activities of people designing new tokamaks using technologies and materials which maybe didn't exist 20 years ago, which maybe indeed can have, can really push the envelope on some of these things, and hopefully bring fusion to us as a source of electricity more quickly. So
Thank
definitely
you.
everything
Yeah,
around
my
materials is
apologies
extremely
for
important.
My apologies for asking a question that was perhaps a little off topic, but we always hear
No,
that
I'm very happy to
fusion
answer.
is 20 years away, 20 years away, and we've been saying that about AI, and it's getting closer and closer, and always feels like we're 20 years away. So that was kind of the origin of the question, but thank you.
Thank you. And I have to apologize. I've overlooked Dr. Shaw. And Dr. Felici, is it okay if she asks
Yeah, that's
you
okay.
a question? Thank you so much for your
No problem.
generosity. Okay, Dr.
Thank
Shaw,
you
the
so
mic
much.
is yours.
Thank you so much, Victoria and Federico. That was wonderful. Talk. So my question is about the multi-domain plasma demonstration that you just mentioned, and also in a part of that, you said that two separate plasma exist within the vessel simultaneously. So my question is about what about the plasma disruption? Do we have this situation? In this model that you just explained, because we know that we have sometimes it's happened, and as a part of the, reactor, a good reactor should have some kind of configuration. We know about this part. So do you have any thoughts around that?
Yeah, so maybe I could separate the question. So the plasmas where we have two plasmas at the same time, this is really something we're doing for scientific exploration to try to understand what happens when you have these two and when you try to merge them slowly together. Is really scientific experiments. And yes, indeed, in these plasmas we do have disruptions. So disruptions mean that the current in the plasma is terminated very quickly, and the plasma just disappears because it just cools down and is no longer stable. And in TCV, in the smaller reactors like TCV, that's really not a big deal. This is something that all the materials in the reactor can deal with this without any issue. This is not a big problem. That's why we're free and have the flexibility to explore all of these fancy new configurations without being afraid to actually damage anything. So that's the first part. And the plasma with the double plasma, we don't know whether it has any advantages or not from the point of view of the disruptions. We simply don't know, and that's part of the scientific curiosity and of the scientific investigation to try to find that out somehow. Now, the other question about disruptions in a more general way in nuclear fusion reactors, in tokamaks in particular, disruptions have for a long time been recognized as one of the things we need to be worried about in the reactors, fusion reactors in the future. So we have to be careful how we design the control systems to be able to deal with them. Now, of course, there's a lot that you can do in terms of actually operating your tokamak, so operating your plasma far away from the operational limits where it might be more likely that such a disruption can occur, right? You can operate in a very conservative way and maybe keep the plasma pressure low, and then you're sure that this is very unlikely to happen. So you have some kind of a margin of some kind of a control margin, and you're sure you don't reach these kind of limits. But that being said, you don't rely only on the control system to protect yourself against these kind of plasma disruption. There's all sorts of different systems which, in case that something goes wrong in the control, can still make sure that the plasma is terminated in a way that does not, let's say, cause any damage to the actual reactor. And I should also stress again, because often this is a source of confusion and misunderstanding, that the worst thing that could happen if all these systems would fail, again, they are all designed as engineering systems to not fail and to always be able to avoid any kind of damage to the reactor. But the only bad thing that could happen is that some parts of the reactor may become damaged. There is no real scenario or no real case in which any kind of damage or harm could come to, the environment or to surrounding people working close to the tokamak or things like that. That's really not something we need to worry about, simply because of the nature of nuclear fusion is that whenever anything happens that goes wrong, the plasma just immediately stops. It's incredibly hard to maintain a fusion plasma, so as soon as anything goes wrong, the reaction will just stop and everything will be okay. Again,
So
it is
no
important.
alien wormhole, right?
No
So
alien
no alien
wormholes,
wormholes.
no nuclear meltdowns, no black holes either, as far as I know. So no, all of this is going to be really okay. Again, the disruptions are a concern for making sure that you can actually operate your reactor and that nothing in the reactor will break. But this is a topic of very active investigations, and for ITER, for example, we do have engineering solutions now, and some of them are being tested more extensively in existing reactors as we speak. We do have solutions for all these things, but it is indeed a serious concern. And the stuff I've been showing today, the axisymmetric control, so that the magnetic control using the magnetic coils is, let's say, the first line of defense against for avoiding these disruptions, while many other layers of protection around that exist on top of this. So maybe interesting to say, at this point in time, if somebody asks me, would you let the AI control the entire tokamak and do whatever it wants to do, I would say no. I would say you can use AI to optimize the operation of a given reactor, but always within the context of having other much simpler systems, which would actually make sure that even if the AI or whatever controller does anything completely wrong, that the plasma is still terminated in a way that doesn't cause any kind of damage. So I think that's very important to say, also to take away some of the concerns that AI has now learned to make a nuclear fusion and will turn against us in some way.
Perfect, thank you.
So, would you be so nice to pinpoint the references that specifically about the two neural nets, the critic and the control control neural net?
So this is all mentioned in the paper. I think the detail of that is mentioned in the paper. So page in the Nature numbering 415 talks about the actual learning and training architecture. And let me see if I can find the details of the neural network architecture. Yeah, that's in the supplementary article data. So that's page, there's no numbering here. It's like 420. Yes, in the
Thank you.
methods text section, there's a part about the neural network architecture, which explains all of that. And there's many references to how all of these things are done in the paper.
Thank you, Dr. Felici.
Great, thank you
You've
very
been
much.
so clear. And yes, Hanson, you will find everything is there in his paper, as well as there were a few links that were posted in the chat before you arrived. So thank you for coming, Hanson. Thank you very much, everyone. And Katarina, I will let you close us out.
Yeah, thank you so much, everyone, for coming and asking all these great questions. And the special thanks, of course, to you, Federico, for taking the time and coming here and for doing your amazing research that will hopefully save humanity. So the last question is, how long until we can do all the carbon capture and have all the energy we need to fix all of our issues? What is your... That's my last question. What do you think? How long it will take?
Yeah, thank
I'm
you.
sorry.
That's okay. That's a question that I get quite regularly. Not only on occasions like this, but also when I talk to my friends or to people I meet somewhere. They always want to know, how far are we from having nuclear fusion as a way that can solve all of our energy needs. The answer is I don't know, and the answer is I think nobody knows. Um, I think I'm getting more optimistic, let's say, these last couple of years, because of indeed this convergence of various things. There's all these advances in the high temperature superconductors, which are very interesting and very good. There is all the work on the construction site for ITER, which is finally starting to converge and to come to something which is going to be completed and is going to operate in the next couple of years. These new results from the jet tokamak, for example, and also I want to stress all the incredible efforts around trying to understand all of the physics that's going on in the fusion reactors, which really means that now we can predict much better than we could 10 years ago or 20 years ago what happens inside the tokamak, inside the fusion reactor. And then now bringing in also these fantastic artificial intelligence advances, which really enable new ways of thinking about problems, new ways of solving problems, new ways of optimizing things. All these things means that I actually see a kind of acceleration now in this work. So I don't know. It's not going to be in 5 years for sure. Maybe not in 10 years, but after 10 years, I don't know. It could go much more quickly than we expect. Also, because a lot of it really depends on how much effort and how many resources various groups, both privately funded initiatives and government funded initiatives, how much time and how much priority and how much resources these are going to have. And I think as we get more scientific breakthroughs with getting better results on the existing reactors or better simulations, the more incentive there will be also for various people, various entities to actually invest in this technology. And then we may see a very fast acceleration, and this could come relatively soon. I also want to say, sorry, the answer is now getting very long, but I also want to say that it's not like one day you're going to read in the newspaper that we have the fusion reactor and everything is done. It will go in steps. First, there will be the first fusion reactor, which generates more electricity, more power from coming out of the plasma than what we're putting in. Then there will be the whole work, which might take another many years to get from that demonstration in a scientific experiment in a laboratory, like ITER will be an experiment, then to get to the stage where you can actually make a prototype of an actual commercial fusion reactor, which really makes electricity and puts electricity on the grid. That's another step which might take many years from the first scientific demonstration. So, and then from the first reactor prototype to having it everywhere available and coming out of your electrical socket, that might take still much more time, right? Like the invention of electricity was something which happened. The invention of electricity, between the invention of electricity and having everybody in their homes having electricity from their plugs, took a long time, as you know. So this is all going to take a very long time, and we shouldn't use fusion as an excuse to not do anything about fossil fuels, reduction of fossil fuel use, renewables with the technologies which already exist. We shouldn't be like in Star Trek, hoping that this technology will fix everything now. certainly not within one TV episode. So as sometimes happens there, we really need to think of fusion as a really long-term thing, as a thing for future for maybe the second half of the 21st century and for the 22nd century and for the future of humanity for many centuries. And in the meantime, we should make the right decisions right now to do what we can with the technologies that we have now and take care of the planet without waiting for fusion to come along and fix everything.
I would say that one thing that is probably limiting is the seasons of funding by governments. So governments tend to have a decade-long seasoning spans of support. So, for example, the last 10 years was AI research, and now we have all this AI progress. So, if anyone here does want to support this kind of work, one of the things that I found is quite effective is contacting your senator, your member of parliament, your government representatives, or even your king, wherever you find yourself in the world, and say you want to support this kind of research. It shows, promise. There's energy independence, kumbaya, all that stuff. So I think that's something that often does tend to sit on the back burner, but that actually makes some of the biggest decisions whether this kind of work gets supported. So if anyone here has the ear of the government or would like to do that, please go ahead. I know I sure will. Thanks.
Thank
Thank
you.
you, Eric. Thank you. I really appreciate when people remind all of us that we need to be active and use the power that's in our vote and our voices and help register people to vote. And wherever you are, stay active, vote down ballot, even for members of your school board. So thank you, Eric. I appreciate that so much.
Yeah, I imagine that it's in the interest of governments to be the first also. I mean, whoever develops this first wins, right? Right now. It's the same as with quantum computing. So, yeah, I hope you get a lot of funding, more than you need, which is never the case.
Thank you. Yes, and it's not only funding we need. It's also we need also good people and good scientists. As I said, I'm now 39. Actually, tomorrow I'm turning 40 years old, but I'm still relatively young here in the fusion community. And we need, because this is a generational effort. As I said, since the 1960s, people have been working on this, and I'm sure in 30 or 40 years from now, people will still be working on some aspects of fusion. Means we need this continuous stream of new scientists, new engineers coming into this kind of field. So studying math and science in high school, and then choosing a career path in science, and and then choosing to work for example, for nuclear fusion or other things to help the environment, or to point to renewable energy in the long-term future. I think that's also a very important part of the story, that in the end, no amount of government funding can help in the long term if you aren't able to school and to educate the people who actually have to do this in the longer term, and to maintain this kind of work, not only in fusion but in all aspects of technology and of engineering.
Yeah, I totally agree. And one part of it is to make science look more attractive again, and something interesting and exciting. And also, it's a very interesting lifestyle, and a lot of the kids don't realize you get to travel a lot, you get to speak in conferences all over the world. It's kind of a very different lifestyle, and yeah, and we are trying here with Science Society to contribute to have a more accurate image of science and scientists. And yeah, that's why we do this here. So, and hopefully this brings an awareness, and that people support more STEM in schools, and especially also for girls, right? I'm also very interested in having girls being like actively involved in science, and interested in supporting them. So my daughter and I,
Absolutely.
we write like kids books for girls that are related to science, and the small girl, that's my daughter's name, because I realized, at least in the US, the kids' books uh, with science content are mostly designed in a way that's attractive for boys, but not for girls. So the girls always choose like stupid books with princesses and unicorns, and it's a big difference already there when they just start reading what they read. Like my boys always bring home like dinosaurs and all spy related stuff. It's always with information, and the pink books are always stupid books. So we are trying to help change that, but this is on a bigger scale. So I hope, please come back with any updates, or if you want to talk about your research again at some point. We are always happy to have you here and help you maybe recruit more people. And thank you everyone for coming, and spread the word, and come back. We'll have more guest speakers here this week. If you're interested, go on the little greenhouse symbol that you will see. Either you just follow the club or check on the schedule. So we'll actually have today at 9 p.m. Dr. Bolton. She will talk about mental illness due to early life stress and glia dysfunction. And then we'll have on Wednesday Dr. Bolani talking about gut bacteria associated with personality traits. And on Thursday we have a rejuvenation room where Dr. Gabeline was successful in mitochondria transplantation between living cells. That's kind of a key thing that was missing in rejuvenation. And then we'll have biomolecule mixes and how they communicate, interact, and adapt independently. And we'll have using molecular orbital-based machine learning by Dr. Cheryl Cheng. So come back, and if you're interested in these type of talks, and thank you, Federico, again for coming. This was an outstanding, amazing room, and your research is so important. So thank you. We really appreciate it, and we are honored.
Thank you very
Very
much
much,
for
Doctor.
having me. It was an honor and a real pleasure to speak to you all, and I really enjoyed it.
Okay,
Thank
thank
you
you,
very
everyone,
much.
and close the room in 3,
Thank
2.
you, everyone.
Bye,
Goodbye,
everyone.
everyone.